Okay, so now we want to discuss the relationship between Gm, the free energy per mole, which is a function of the concentration, and the chemical potentials, mu A and mu B. Okay, so let's say we have a graph of the free energy per mole, Gm, as a function of the concentration xb. So over here we have pure B, over here we have pure A, right? So if we looked at a graph like this and we plotted this free energy per mole, typically we would get a curve that might look something like this. Okay. So we know that it should be lowest in the middle because entropy reduces the free energy when we mix things, and then higher on the ends. And if we look at any particular value of xb, so let's say we pick a concentration here, xb prime, right? We could read off a value of gm that's appropriate for xb prime, and it turns out what we can do at this point is draw a tangent line that goes through xb prime and is tangent to gm, right? And we could extend that in both directions. Here I'm going to extend my axis down this way. And we could read off numbers from these two sides. And it turns out that the numbers we read off from this tangent give us the chemical potential of B at xb prime and the chemical potential of A at xb prime. Now this is of course very useful, right? It tells us that there's a sort of graphical interpretation that allows us to read off the chemical potentials for each of these curves. It also tells us that as we're moving through concentration space, if we were to lower the amount of xb, we would be changing the chemical potentials of xa and xb. So if we moved, let's say, to lower xb prime here, we would be lowering the chemical potential of mu b, the chemical potential of B, and we'd be increasing the chemical potential of mu A, of A. So how can we show that this is the case? Here I've just asserted it, I haven't demonstrated it, but let's first start by let's think about what Gm and its derivatives. So we know that dGm, right, the differential of Gm, must be equal to mu A times dxa plus mu B times dxb. That is, the chemical potentials give us the change of the free energy per mole with respect to a change in the amount of one species or the other, so we can get the change of the free energy per mole by looking at the chemical potential times the change of each particular species. But if we have a mixture of just A and B, we also know that dxb is equal to minus dxa, right? Because if we decrease B, we increase A, and vice versa. So if we consider the slope here, right? What is the slope of dgm dxb? Well, we could rewrite our dgm as mu A minus dxa, minus dxb, plus mu B dxb, so we could write this as mu B minus mu A dxb, right? So as a consequence, dgm dB at xb prime at this particular point, we can write that as just mu B at xb prime minus mu A at xb prime. Okay. So the slope here is related to the difference in the chemical potentials of A and B. Okay, so now let's say we want to write an expression. So let's write an expression for the tangent line. So we know it's a line, so we can write it as y equals mx plus b, right, where m is the slope and b is the y-intercept. And we know that the slope m must be equal to mu b xb prime minus mu a xb prime, right? But how are we going to get the intercept, right? So, well, we can write b must be equal to gm at xb prime, right, so the value here, minus the slope times xb prime, right? So we just are going to take this slope, minus the slope, and track it back to where xb prime is equal to 0, right? And we know our m value, right? So we can say b must be equal to gm xb prime minus mu b xb prime minus mu a xb prime times xb prime. Okay, so that means we can write our expression for our line as y equals the m, the slope, mu b xb prime minus mu a xb prime times xb, right? That's our x. And then minus or plus b, so we're going to add this, which is another mu b minus mu a minus xb prime, so we can write this as xb minus xb prime, and then we have our plus gm at xb prime. Okay, so this is our expression that gives us the equation for this line. Okay, so now we want to have this, but we have this now in terms of gm xb prime. We want an expression for gm xb prime. So let's use the fact that we've defined that dgm dxb at xb prime must be equal to mu b at xb prime minus mu a at xb prime. And so we can say that let's change colors, xa prime times dgm dxb at xb prime, that's just xa prime times this, is equal to mu b xb prime xa prime minus mu a xb prime xa prime. Okay, that's pretty simple. We just multiplied through by xa prime. And since we also know that gm at xb prime must be equal to mu a at xb prime times xa prime plus mu b at xb prime xb prime, right? We can say that if we take the value of gm at xb prime and we add xa prime times dgm dxb at xb prime, right? That's going to be equal to, now we're just taking this expression, right? So we have mu a xb prime xa prime plus mu b xb prime at xb prime xb prime, and now we're adding this expression, so we have plus mu b xb prime xa prime minus mu a xb prime xa prime, right? So these mu a xb prime xa primes will cancel, right? And what we're left with is just simply mu b xb prime times xb prime plus xa prime, and that has to equal 1, right? Because if we add the two mole fractions, we just get 1, so that gives us mu b xb prime. Okay, and so this shows us at this point that here what we were doing is taking the value here and adding xa prime, which is just the distance on this side of the dashed line, times the slope. So that's showing us that the value at xb equals 1 is equal to mu b xb prime. So we can just continue this line of reasoning and say that, okay, so now our expression for y of our line is, so now we're going to use our expression for gm. We can write this as mu b xb prime minus mu a xb prime times xb minus xb prime plus, and now we put in our expression for gm, which we're going to write as mu b xb prime minus xa prime times dgm dxb at xb prime. So mu b at xb prime minus mu a at xb prime. Okay. So this is dgm dxb evaluated at xb prime. And if we simplify this, we can write this as mu b at xb prime minus mu a at xb prime times, and now we're going to combine this with this piece. So we'll get xb minus 1 plus, and now we have this mu b xb prime, right? So we get at the end y is equal to mu b xb prime minus mu a xb prime times xb plus mu a xb prime. Okay, so what does this tell us? It tells us that if we set xb equal to 0, obviously y is equal to mu a at xb prime. And also we see if we set xb equal to 1 at this end, as we showed before, here we'll get minus mu a b at xb prime plus mu a at xb prime, so those will cancel, so we'll get y is equal to mu b at xb prime. So we've shown, as I stated at the beginning, that if we look at this slope of this line and we trace it to the endpoints, we can read off the two chemical potentials.